In most cases, the first step in solving a differential equation consists of transforming it into another equation by means of a substitution. So, suppose that we wish to transform the equation dy dx equals f of x y using y equals g of x u of x. Where that u is a function of x. Now, if g possesses first partial derivatives, then by the chain rule, we would have dy dx is equal to partial g partial x times dx dx plus partial g partial u times du dx. Now, this is just simply 1. So we can rewrite this as gx xu plus gu xu times du dx. Recall that this is just another notation for partial derivatives. So this is notation for the partial of g with respect to x, and this is the notation for the partial of g with respect to u. If we now make all of the substitutions, then the differential equation dy dx equals f of xy becomes g sub x of xu plus g sub u of xu du dx is equal to f of x comma g of xu. If we solve this for du dx, then du dx becomes a form capital F of x comma u. So if we can determine a solution u equals phi of x, then a solution of the original differential equation is y equals g of x phi of x. We will now look at a few instances where we use substitution. We now look at homogeneous equations. So if a function f possesses the property f of tx comma ty equals t to the alpha times f of xy for some real number alpha, then f is said to be homogeneous of degree alpha. A first-order differential equation, m of xy dx plus n of xy dy equals 0, is homogeneous if both m and n are homogeneous of the same degree. Now, let's suppose that m and n are homogeneous of degree alpha. Then we can write the following. M of xy is equal to x to the alpha times m of 1 comma u, and n of xy is equal to x to the alpha times n of xy. I'm sorry, not xy, of 1 comma u, where u is equal to y over x. We also could write m of xy is equal to y to the alpha m of v comma 1, and n of xy is equal to y to the alpha. Let's make sure that that is an actual alpha and not a 2. N of v1, where v is equal to x over y. So these two imply that we can rewrite the homogeneous equation using substitution. So we're going to look at using this form here. So we can rewrite m of xy dx plus n of xy dy equals 0 as x to the alpha m of 1u dx plus x to the alpha n of 1u dy is equal to 0. Which can be written by dividing everything by x to the alpha as m of 1u dx plus n of 1u dy is equal to 0. Now again, remember we have u is y over x, so this means that y is equal to u times x, which means that dy is u dx plus x du. So now we take this and replace this dy with it. So m of 1u dx plus n of 1u times u dx plus x du is equal to 0. We now go ahead and simplify this to give m of 1u plus u times n of 1u dx plus x n of 1u du is equal to 0. Which becomes dx over x plus n of 1u du divided by m of 1u plus u n of 1u is equal to 0. So let's go ahead and solve the differential equation x squared plus y squared dx plus x squared minus xy dy is equal to 0. So m is x squared plus y squared. So m of tx ty is tx squared plus ty squared. So t squared x squared plus t squared y squared. This is t squared times x squared plus y squared, which is t squared times m. So m is homogeneous degree 2. N of xy is x squared minus xy. So n of tx ty gives us t squared x squared minus t squared xy, which is t squared times x squared minus xy, which is t squared times n. So n is homogeneous degree 2. So this is a homogeneous equation. So we let y equal u times x, which means that dy is equal to u dx plus x du. So we take our original equation and we can rewrite it as x squared plus u squared x squared dx plus x squared minus ux squared now times the quantity of u dx plus x du is equal to 0. We need to simplify this some more. So we are now going to FOIL this. So we're going to get u x squared dx plus x cubed du minus u squared x to the 4th dx I apologize, I don't know where I got that x to the 4th from. That's just x squared minus u times x cubed du is equal to 0. What we now wish to do is bring all of our dx terms into one grouping, all of our du terms into another grouping. So x squared plus u squared x squared minus ux squared minus u squared x squared dx plus x cubed minus ux cubed du. Well, that's nice. The u squared x squareds will cancel out. Factor out an x squared from this first grouping. We have x squared times 1 minus u dx. We can now factor out an x cubed. We get 1 minus u du has to equal 0, and so did that up there. I apologize, this should have been a plus, which means this is a plus. Okay. We now divide everything by 1 plus u, and also divide everything by x cubed. So we get x squared over x cubed dx plus 1 minus u over 1 plus u du is equal to 0. Which of course becomes dx over x plus 1 minus u over 1 plus u du is equal to 0. Now we're going to go and integrate. To do this, we first want to rewrite 1 minus u over 1 plus u. So this is done using either synthetic division or polynomial long division. I'll leave that work to you. This will become dx over x plus the quantity of -1 plus 2 over 1 plus u du is equal to 0. We can now integrate everything. So we're going to get the natural log of the absolute value of x minus u plus 2 times the log of the absolute value of 1 plus u is equal to a constant. Now replace u with y over x. Remember, trying to find y. So we're now going to solve this for y as much as we can. So let's simplify some more. So we get log absolute x minus y over x plus 2 times the log of the absolute value. We're going to write this as a single fraction, so we get x plus y over x is equal to c. Now applying law of logs, we can write that final log as the log of x plus y squared all over x squared is equal to c. We can once again use laws of logs. We can write this as negative y over x plus the natural log of x plus y squared over x is equal to c. So this would mean that the natural log of x plus y squared over x is equal to y over x plus c. Getting rid of the log, we can write x plus y squared over x is equal to e to the y over x plus c, which is just simply c times e to the y over x. Now multiply both sides by x, and we have x plus y all squared is equal to cx e to the y over x. There's going to be no way to explicitly solve for y, so we can just leave it in that form. An equation that is in the form dy dx equals p of x y plus q of x y to the n is called a Bernoulli equation. Now, for the cases n equals 0 and n equals 1, we can clearly see that the Bernoulli equation is linear. For any value n greater than 1, or rather, excuse that, just for any value of n that's not 0, 1, we'll use the substitution u equals y to the 1 minus n. This, of course, means that du dx is equal to 1 minus n y to the minus n dy dx. This, of course, means that y to the minus n dy dx is equal to 1 over 1 minus n du dx. Let's put these substitutions into the Bernoulli equation. So the equation becomes, well, I'm sorry, we're not plugging in yet. We're going to multiply our Bernoulli equation by y to the minus n. This will give us y to the minus n dy dx equals p of x y to the 1 minus n plus q of x. Now if we do the substitutions, this will give us 1 over 1 minus n times du dx is equal to p of x times u plus q of x, which means that du dx is equal to 1 minus n times p of x u plus 1 minus n times q of x. And we can see that this is linear in u. Let's now look at the initial value problem. Y prime equals negative 2y plus e to the x y cubed with the condition y of 0 is equal to 1. Now we can clearly see this is Bernoulli, with p of x equal to negative 2, q of x equal to e to the x, and n equal to 3. So we're going to use the substitution. U equals y to the minus 2. This means that u prime is equal to negative 2y to the minus 3 times y prime. Multiply the original equation by y to the minus 3, and we get y to the minus 3 times y prime is equal to negative 2y to the minus 2 plus e to the x, which means that u prime is equal to negative 2 times negative 2u plus e to the x, which is of course equal to 4u minus 2 e to the x. So this becomes u prime minus 4u is equal to negative 2e to the x. Now we can see that this is linear in u, so we use the techniques for solving linear equations, which means we need to find an integrating factor. Now, the integral of negative 4 dx is negative 4x. And so our integrating factor mu is e to the negative 4x. So we multiply our equation by mu, and we get e to the negative 4x times u prime minus 4e to the negative 4x u is equal to negative 2e to the negative 3x. This means that d dx of e to the negative 4x times u is equal to negative 2e to the negative 3x, which means that e to the negative 4x times u is the integral of negative 2e to the negative 3x dx, which is equal to 2/3 e to the negative 3x plus a constant. So this means that u is equal to 2/3 e to the x plus ce to the 4x. However, u is y to the negative 2. So this means that y to the negative second power is 2/3 e to the x plus ce to the 4x. And so y is 2/3 e to the x plus ce to the 4x raised to the negative 1/2 power. And of course, this should be plus or minus. So y is plus or minus 1 over the square root of 2/3 e to the x plus ce to the 4x. We can now apply the initial condition, which was y of 0 is equal to 1. So we get 1 is equal to plus or minus 1 over the square root of 2/3 e to the 0 plus c e to the 0. So 1 is equal to plus or minus 1 over the square root of 2/3 plus c. Now, this can't be negative, which means this value here is always positive. That means I can get rid of this plus or minus. It has to be a positive value. So 1 is actually equal to 1 over the square root of 2/3 plus c. This means that 1 has to be the square root of 2/3 plus c. So 1 is 2/3 plus c. This means that c has to be a third. So our particular solution is plus or minus the square root, 1 over the square root of 2/3 e to the x plus a third e to the 4x. So we get plus or minus 1 over the square root of 2e to the x plus e to the 4x all over 3, which is plus or minus the square root of 3 over 2e to the x plus e to the 4x. And so our solution, we would write y of x is equal to plus or minus the square root of 3 over 2e to the x plus e to the 4x. If we have a differential equation of the form dy dx equals f of ax plus by plus c plus d, where a, b, c, and d are constants, they're real numbers, with b not equal to 0, then we can reduce this to separable variables by using the substitution u equals ax plus by plus c. We consider the differential equation dy dx equals the quantity of negative 2x plus y squared minus 7. So we're going to use the substitution u equals negative 2x plus y. This gives u prime is equal to negative 2 plus y prime. So we can rewrite our differential equation as u prime plus 2 is equal to u squared minus 7, which is u prime is equal to u squared minus 9. So du dx is u squared minus 9, which means that du over u squared minus 9 is equal to dx. This gives us the integral of du over u squared minus 9 is equal to the integral of dx. Evaluating that integral on the left will give a sixth natural log of the absolute value of u minus 3 minus a sixth natural log of the absolute value of u plus 3. And then, of course, this will equal x plus a constant. We can rewrite this as a sixth natural log of the absolute value of u minus 3 over u plus 3. Which means that this natural log is equal to 6x plus 6 times a constant is still a constant. And so we have u minus 3 over u plus 3 is equal to e to the 6x plus a constant, which is just a constant times e to the 6x. Multiplying both sides by u plus 3 gives u minus 3 equals c e to the 6x times u plus 3 c e to the 6x. Putting all of the terms that have a u on the left-hand side and every other term on the right-hand side, we'll get u minus cue to the 6x is equal to 3ce to the 6x plus 3. Factor out that u, we get u1 minus ce to the 6x Now, divide by the 1 minus ce to the 6x, and we get u is equal to 3ce to the 6x plus 3 all over 1 minus ce to the 6x. Or we can factor out that 3 and be left with ce to the 6x plus 1 all over 1 minus ce to the 6x. But u was equal to negative 2x plus y. So this means that negative 2x plus y is equal to 3 times ce to the 6x plus 1 all over 1 minus ce to the 6x. And so our solution y of x is simply 2x plus 3 times the quantity of ce to the 6x plus 1 all over 1 minus ce to the 6x.